Three, 2, and 1. All right, you guys have your notes open and ready to go? Thanks for checking in with each other. It's always a good thing to do. Ready? What does log base 2 of x look like?
It's like
a swoopy swoop, right? What did exponentials look like? Yeah, but it was a very different. Well, was it that different? Not really. Why does it make sense that what one's doing, the other is doing? Wait a minute. So if I was to graph log base 2 of x, no, I'm sorry. Exponential y equals 2 to the x. Why does it make sense that log base 2 of x would look like this? They're inverses of each other, and if they're inverses of each other, what do they reflect? We're dabbing it. What do they reflect across? Which is what's exciting.
X plus 1.
Ooh, which line? Y equals x. Wrong spot.
That was close. Come on.
And it still turned green.
I'll take it.
That's okay. So it reflects across the y equals x line, right? So really quickly, we're going to actually keep the blue one and just, not the blue one. This is a struggle, my colors. We're going to keep the red one. But first of all, let's review really quickly what we know about 2 to the x, then we're going to erase that one. So this one is the first one that you guys should have graphed, log base 2 of x. How were you able to do that in your calculators? What function did you use? Math? Scroll all the way down to log base. But what about, help us out, what about those poor people with the yellow button on their calculator? It's kind of the older version, it's a non-updated operating system, and they can't fix it. There is a workaround. What's the workaround that they could have used?
Log blank.
The change of base formula, the division thingamabob, and they could have used ln of who for log base 2 of x? Who do you put on top? The x. So you could have done ln of x over ln of 2, or common log of x over common log of 2. Same thing, my poor people with the yellow button. But coming back, what would this point be of the log base 2 of x?
0.
Can you guys tell? Can you like eyeball it on your graph? No? Well, let's review with exponential. Question, kiddos, with exponential functions, when x was 0, what was y? What was this point?
0.
Anything to the 0 power is?
1. 0. 1.
Right.
It's Monday.
It is a Monday. So if an exponential function has this point, what's the logarithmic function going to have? What happens with inverses?
1, 0.
They switch. So I can say this is the point 1, 0. Question. What kind of asymptote did the exponential function? Oh, it didn't have that, did it? It had a horizontal asymptote, but a horizontal asymptote where?
0.
At, I must have put a lot of little dots there. Oh, struggle. Don't worry, they're slowly disappearing. One more. There we go. Exponential functions had a horizontal asymptote at y equals 0, so question. What's the logarithmic function going to have at x equals 0? A vertical one. Yep. See, everything just switches. Instead of a horizontal one at y equals 0, the logarithmic is going to have a vertical one at x equals 0. Instead of the point 0, 1, the logarithmic is going to have the point 1, 0. And technically, exponential functions, remember to move and shift and transform, we always want a couple points at least. So we use the point 0, 1. Plug in 0, 2 to the 0 is 1. That's easy. Plug in 1, 2 to the 1 is what? If you plugged in 1, this one should have been at 2, right? So if the exponential has the point 1, 2, question, what will the logarithmic one have? Point 2, 1. And I'm going to go ahead and get rid of all the exponentially stuff, because we were just using that to build up the logarithm. So now my next question is soon going to be, what changed as soon as the base was no longer, what changed as soon as the base was no longer 2? Well, that didn't work the way I wanted it to. What changed as soon as the base was no longer 2? Because you guys graphed a few logarithms, right? So, question, what changed with ln? Because you guys graphed them all at the same time, true? y2. y1 graph, what happened with y2? Did it get taller or shorter? Oh. Really? A lot or a little? Why just a little? Who's his base again? Ooh, not ln. This one's 10, but close. E, and E was what? 2.71828? Oh, that's pretty close to who? But still, we can say, well, if he got a little bit, I think, wasn't he technically a little bit above, and now he's technically a little bit below? Is that how he went?
Yes.
So it's kind of like he's being dilated a little bit, right? Like squished a little bit, like compressed a little bit. He's being compressed a little bit. Now hold on, what happened when you graph the common log? Because all of a sudden that's log base 10. That's a huge jump. Being steeper or getting more compressed? Yeah. So what happens the higher the base goes? The flatter the logarithm gets. So, we're not going to talk, just like we did with exponentials, we're not really going to talk about dilations because even just changing the base stretches or compresses the graph. Here's my question. How would you make the logarithm get steeper then? Okay. Can we experiment for a second? Can you guys go to your grapher? What would go lower than 2?
-2.
We could try 1. So that graph's going to be a little funny. Try 1.
Isn't it just the
1 to any power is still 1. That should be a flat line. Struggle. So I don't think logarithms can really have a base of 1. I mean, they can, it's just kind of boring. What's something smaller than 2 that's not 1?
1.5?
Okay, try a negative. What happens if you do log base negative 1 or negative 2 or negative 5? Yeah, why? Negative numbers raised to powers, don't they go back and forth between negative if it's an odd power, then positive if it's an even power, then back and forth and back and forth and back and forth? They're not a nice continuous function, so actually even numbers are bad bases and are kind of not allowed either. I heard someone say it. What's something that's lower than 2 but not 1 and not a negative number? 0.5. Try 0.5 or try 1/3 or try 1/10. We're getting smaller, but we're not going negative, and we're not using 1, which is kind of boring. Boring. That's not good. Those of you who don't have a calculator, you have to go on faith. But what happens, guys, as you do base 1/2 or base 1/5 or base 1/10? It's a little bit steeper?
Turns upside down.
Turns upside down. There's my calculator. Missing. Why would he go upside down? Now we're trying so stinking hard, and at least we got something that existed and something that works. Let me get rid of my calculus stuff for just a second. Let me get to Zoom Standard so it's not weird. I know, we're doing a quick discovery, but why on earth, when we do math, and then we do log base, which is oh, there he is, A. We thought for sure we'd have it for 1/2 or 1/10 or 1 whatevereth. So why is he all of a sudden looking a lot like a, what? He's been flipped. How has he been
1/2.
Log base 1/2 of x, let's say it equals y. Do you guys remember how to look at this as an exponential? Log base, 1/2 is the base. Who's the power? Y. Oh, isn't that 2 to the negative? Oh, tricky, tricky, tricky. It's like a negative power hidden. We didn't even see it. So another way of writing this is weird, but we could have written this as log base 2 of x equals negative y. Because 2 to the negative power is the same thing as 1/2 to a positive power. Okay, well, all that to say, long story short, the 1/2 didn't work. You guys were kind of on the right track. The way to be less than 2 and not a negative and not 1 and not something less than 1. What if we were to use something like 1.1? Anybody try that? A fraction, but a fraction that's not less than 1? Oh, hey, look, you stretched. Really stretched, actually. 1.2, 1.3, 1. Et cetera, et cetera, et cetera. So anyway, all that to say, logarithms can get kind of funny, especially when they have bases that are fractions in between 0 and 1. We saw that with the base of 1, that was like a boring flat line. That was kind of weird. Negatives don't even work. So all that to say, there are some special rules to logarithms. We have to be careful that we're following those rules. But let's get back to normal logarithms. We're trying to look for weird ones. Now we're just back to the normal ones. Log base 2, log base e, log base 10, log base 7, log base... What's in common with all of these? Okay, they all have a log. Let's think about the graphs though. How far left do all of the normal ones go?
Infinity.
Ooh, I don't think so.
Positive infinity.
Zero.
How far left?
Oh.
I heard it. Zero. Right? What's going on at 0 that's saying, not getting past me? There's a vertical asymptote. So I can say my domain for all logarithms, all normal logarithms, even the ones that we flipped, still the domain, x had to be greater than 0, or another way of saying it is 0 not including to infinity, right? For interval notation. There's a vertical asymptote at 0. Well, we can't include it, so we're going to do parentheses instead of bracket. We can skip down here to vertical asymptote and say, yeah, there's a vertical asymptote at x equals 0. Right? Range, how low does he go?
Negative.
He goes all the way, right? So negative infinity. And then how high does he go? Yeah, but does he go the same speed, faster, or slower than the exponential that we had up a little bit ago, the green one? Slower, right? Because exponential growth is super fast. That's why a lot of people talk about something growing exponentially, plus it happens in nature a lot. But logarithmic growth is still going up, but not near as fast. So I'll have to say it is going to infinity, but a different level or magnitude of infinity than exponential. Some of your minds are working fast saying, wait a minute, I thought infinity was infinity. Kind of. X-intercept, where does it hit?
1, 0.
1, 0. Strictly monotonic, meaning it's strictly increasing as you go from left to right on its domain. It doesn't decrease unless there's a reflection. And then like exponential at the very, very bottom, he's continuous, no holes, no vertical asymptotes within his function. Yes, there's one bounding on the left, but within him, he's totally continuous the entire time. Can you guys really quickly, in your notes, flip back to section 3.1 and go find where we talked about exponential graphs. We did a page very, very, very similar to this. And you actually had the same characteristics mostly. You had domain, you had range, you had y-intercept. Strictly monotonic, horizontal asymptote. And then continuous. Did you find it? Look at the domain and range that we wrote down for exponential. What's true as compared to this one? It's flipped. Why does that make sense?
Because they're flipped.
Because they're inverses. So just like the points flipped, the domains and ranges flipped as well. Okay, thank you for looking. Come on back. Question. I had 2 special points before we turn the page. I had 2 special points for log base 2 of x. Question. What would be the second special point for y equals ln of x? What would be the second special point for y equals ln of x? I'm going to do this because it's easier. Okay. Does the 2 stay or does the 1 stay?
2. 1. I don't know.
Why? I know, it's okay, it's okay, it's okay. Where did this point come from? If you plug in 2, log base 2 of 2 to the 1, log base 2 of 2 cancels and you just get 1. Question, what would you have to plug into ln to cancel with ln and get just 1? What was ln again? Log base e of, who needs to be there for it to all cancel? E. So log base e of e. Oh! So what's ln going to have that's special? He's going to be a little bit higher, just a little shy of 3. And it's going to be E1. Because you plug in an e to ln, the log base e of e cancels, and you just get 1. You plug in a 2 to log base 2 of 2 to the 1 is just 1. What would you have to plug into y equals common log or log base 10 in order to get 1?
10.
Exactly. So even though we're not going to see him super well, his other special point would be 10, 1. But does that make sense why these keep on getting stretched and stretched and stretched? As the base gets bigger, the point where y equals 1 is going to get further away as well, so they have to keep on compressing. Okay, all that to say, this is how you deal with the parent function of logarithm. Oh, struggle, so how do we transform them? This is how you deal with the parent function. Now we got to transform them. It's like the rain wants to come, but it doesn't. You guys notice there aren't really any dilations here either. It's kind of on purpose. The bases kind of serve as our dilations if we need them, or if nature needs them, or if a certain equation needs it. And as you guys are writing, I want you to think about B, he's being added on the outside. C, he's being subtracted on the inside. A, well, A is the easy one. He's just the what? Log?
Base.
A is just the base. A is just the base. B, adding on the outside. What do you remember? Even though it's a Monday. Vertical, because it's on the outside, and then it's being added, so shift, good. Vertical shift, or the snazzy way of saying it, vertical translation, right? By technically B units, or of B units. C, who is he? Horizontal. Shift, snazzy way of saying it, translation. By C units. I don't know why I abbreviated shift, because I wrote the whole word. That's weird. Okay. So remember, x minus, it's always backwards what you think. X minus 2, it's 2 to the right, etc. Reflections. Reflections across the x-axis, across the y-axis. I'll do the exact same thing I did with exponential, just for my visual ones to remember. If it's across the x, and if it's across, or about, or at, they can say it different ways. The y. What kind of flip will we describe those as real quick? Across the x?
Horizontal.
Oh. X is a horizontal coordinate, but look at it. If it flips like this or like this.
Looks like horizontal.
Oh, it's a vertical one. What's up goes down, what's down comes up. It's a vertical change. I know that's the hard part though. Our brains, especially on a Monday, I caught you. Caught you in the common mistake. Our brain sees the x-axis and thinks horizontal. But you gotta think if it goes about the x, it's actually an up-down change. It's vertical. And then across the y-axis, make that change. Horizontal. It's going left-right. Did you have a question? Yes. Horizontal flip. So then think about it. Vertical, outside. Horizontal, inside. Reflections. How do we get them? Multiplied by a... There we go. So then across the x-axis, just to simplify life and not to show all the different transformations at once, let me go ahead and just write it as, what if you had y equals and there was a negative outside the logarithm? To help us zero in, I'll just show the reflection. And then across the y-axis, a horizontal flip, what if there was a negative where? Yeah, next to the x. Inside the logarithm, but next to the x. Now technically, if you guys were writing notes, there should be one little thing that we left blank, and I don't even think it's on this page.
Reflection.
No, we just filled him in though.
Continuous.
Yeah, but continuous was more of just a fact. What else did we leave blank? Oh, there's a colon. I think we should have written something. Let's take just a second and talk about domain problems of logarithms. If you guys remember, way back in the day, chapter 1. we said there were, and I know it's not going to be on the notes online, but we said there were certain domain problems, right? Do you guys remember the two that we basically had to be especially careful of in chapter 1? What was one of those big domain problems that could happen? Which ones? Denominators. If I have a function, f of x over g of x, I had to be careful because my domain restriction is whenever what occurs?
Denominator equals 0.
Denominator. The denominator equals 0 is a problem, so to find my domain, I have to set the denominator not equal to 0 and solve, right? Whoever was in the denominator, I had to set not equal to. So if I had, for instance, 2 over x minus 2, x minus 2 could not be 0, so x could not be 2, and we would solve. What was another, besides denominators, what was another domain problem? Radicals, but any radical? Cube root? Is he a problem? Can something cubed be positive? Positive, 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 yeah. Can something cubed be negative? What's a negative times a negative? A positive times a negative. Oh, something could be cubed and stay negative. So cube roots aren't a problem, but what are a problem? Square roots, or actually any, you guys remember I put it this way, any even powered or any radical with an even, I guess, index would be a really snazzy way of saying it. If I say any even powered root. So whenever you have any sort of square root of a function, I'll put an n for n as an even number. Remember the domain restriction on him? Whoever's underneath the radical, as long as it's an even-powered root, needs to stay what? Greater than or equal to. It's allowed to be 0. Square root of 0 is 0. 0 squared is 0. 0 is not a problem. Negatives are a problem. Right? That's where imaginary numbers come in. You might not have remembered it, but way back when, the first time we talked about this, there were 2 more, but I said, oh, don't worry, we haven't talked about them yet, so they won't be in chapter 1, and they weren't. And then they weren't going to be in chapter 2, and they weren't. But now, one of them has shown up in chapter 3. Who else has a domain problem? Logarithms. Why? Look at that graph, kiddos. A standard logarithm. What does his domain have to be? 0 to infinity, or a snazzy way of saying it. Let me write it real quick. Log base A of, I'm putting an f of x in there to say, it might be log of something other than x alone. It might be log base A of x squared. It could be log base A of square root of x. It could be log base A of, 3x minus 2. For logarithms, whatever is inside the argument of the logarithm must stay greater than 0. And, more specifically, there's a vertical asymptote at whatever's inside equal to 0. These ones for review. For denominators, for even-powered roots, and now we have our new one of what to do. For logarithms. My snazzy grammarians, I should probably put a semicolon or something to distinguish between the two. Alright, how's that look? So then coming back here, some of you are writing this all down to remind yourselves, and that's a great thing to do. 2 of them are review, 1 of them is new. Over here in our notes, I'm just going to officially denote this for any log base A of f of x. I think before I might have been using u, that's another way to say, might not just be an x alone. The domain problem. f of x must be greater than 0, because there's a vertical asymptote at 0, so it can't equal. Square roots can equal. Logarithm arguments cannot. And then more specifically, there's a vertical asymptote at f of x equals 0. Anyway, that could be a clue to help us with graphing logarithms, because it kind of tells us what the domain should be. Let's go ahead and go graph a couple of these. We're going to start with just a general log base 2 of x. You guys have already seen him. You've already seen a log base 2 of x. So I'm going to use him as our parent function for this one. We already know he has, just like all basic logarithms that haven't been shifted, he's going to have an x-intercept of 1, 0. He's going to have a point at 2, 1. So he's going to be at y equals 1 whenever x is equal to his base. We're going to use a vertical asymptote of 0 at x equals 0, I should say. And then he swoops, just not very fast. He's a concave down swoop as opposed to exponential that are concave up. Which kind of tells us something about concave down slopes and concave up slopes, but that's okay. We'll save that for another time. For g of x, now, we're going to talk about the transformations. And it's going to be good, and it's going to be helpful, but first of all, can someone really quickly look at what's on the board and tell me, what's his domain? Not or equal to, remember that's what.
Or x is
Greater than
0.
Careful. Inside is greater than or equal, no, I said it again. Inside is greater than 0. Solve, which means x must be greater than 1. Because at this equals 0, at 1 is a vertical asymptote. So right away I can actually say, without even thinking about transformations whatsoever, just thinking about my clue about domain, I know there's a vertical asymptote at x equals 1. Quick little cheater trick. But if we were to think about transformations, we should be able to say a few more things, like, oh hey, subtracting 1 on the inside means everything gets horizontally shifted how? Right 1. Good. Remember, minus means to the right when it's inside the argument. And what's that positive 2 being added on the outside indicate? Vertical shift up 2, right? Now, I've already figured out my vertical asymptote. He is where he's supposed to be, right? What am I going to move right 1 and up 2? Not the vertical asymptote. He's solid. He's already gone. His right 1 and up 2 is, well, completely pointless. Yeah, I'm going to use my special points, my x-intercept and then my other point. So I can move him up 2 over 1. I can move him up 2 over 1. And that's going to be the new point. Well, up 2, that's now going to be an over 1. An x of 2 and a y of 2, right? Add 2 to the y, add 1 to the x. And then for my other point, I'm going to also go up 2 over 1. So up 2, that's going to be now a y of 3, and over 1, that's going to be a y of 3. And then, all I have to do is say, hey, there's my vertical asymptote, dun, 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 dun. Might not be perfect, but dun, dun. Now with h. His domain is normal, nothing's changed on the inside, so he still has, or he's still going to have, a vertical asymptote at x equals 0. His domain, nothing has changed. It's still x greater than 0. But now I need to ponder, I see a 1 and I see a minus. What do those mean? Now first of all, be really careful. This 1, it's a positive 1, right? So even though there's a minus next to the logarithm, the 1 is still positive, which should indicate a what? Up 1. But what's the negative outside the logarithm indicate? It's flipped and it's on the outside, so vertical. It's going to flip this away, right? Now, careful with the transformations. We have to be careful with the order that we do them in. Should we shift up one and then reflect? So go up and then reflect down?
No.
Or should we reflect and then shift up?
Flip, then.
Exactly. Start with the negative. Think PEMDAS. Start with the multiplication, then go to the addition. So we're going to have a vertical flip first. And then we're going to have a vertical shift. I'll just say a shift up one. So vertical flip. Well, okay, the 0.10 doesn't really vertically flip anywhere. The 0.21 now becomes the 0.2 negative 1. The y flips, the x stays the same. But he's not supposed to stay there. Where is he supposed to shift? Up 1. Okay, so all of a sudden the point is now here, so that's going to be the 0.20. He flipped down to 2 negative 1. He went up 1 to 2 0. This one, 1 0, flips nowhere. But then he shifts up 1 to the 0.11. And then we see our vertical asymptote, and we have our logarithm. Parent function, one set of transformations in another. Okay? Logarithms, not super easy, but if you use our domain problem trick, it'll help you with the vertical asymptotes. And then the flipping, the translating, hopefully those clues will help that we wrote down. Now, wait a minute. Haven't we already talked about this? What's this talking about? Exponentials and logarithmics are what? Inverses of each other. So if they're inverses of each other, then kiddos, what's going to happen with their graphs? They're going to flip. So, some of you might want to write this down as a further, cementing of, what do inverses do and how are they related? What happens to their points and their domains and ranges, but we've already talked about that. So let's go ahead. This will be in your notes. If you want to write it down, that's great. Let's do one quick homework help before saying, hey, we're done. So one quick homework help before we're saying, hey, we're done. Finally, with 3-2. And we'll check 3-2A and 3-2B even tomorrow. And those of you that did 3-2A over the weekend, don't need to have the homework. Those of you that didn't, well, you have a nice big pumpkin. Have fun. What do we do? They give us a function, y equals ln of x. They tell us a when, and they give us an x. Well, guys, what do we always do?
Plug it in.
Plug it in. So we can say y is equal to ln of who? E to the negative 4. I don't know what that is. Wait. Can't we look at ln as being log base e? I'm putting it in quotes because you're not technically supposed to write this. Does that help? Aren't they inverses? Don't they undo each other? So what should the final answer be? Negative 4. Now pause. Some of you from last year might remember, and this is where we're going to 3-3 tomorrow, that there might be some property that lets a power come down. So then the negative 4 is out here. Log base e of e is just 1. There's another way of getting here, but we'll have to look at those properties tomorrow. Okay, those finish up your homework tonight. Is there anybody to tackle right now? Hopefully we don't get rained on too badly today. I'll see you
Hey, Tyler.
Remind me tomorrow. I'll see you later.